Hi everyone, thank you so much for joining us in the computer vision guest speaker session today. I am replacing Benedict as the host today. We have with us for guest speaker session Jianwei Yang. Jianwei will be talking today about multimodal AI agents for comprehending multi-sensory observation. Thank you so much, Jianwei, for taking out your time, and I'll hand it over to you.
Thank you. Thank you, Ahmed. Let me share my screen. Let me share the screen. Share this screen. So can you see my screen?
Yes, we can.
Awesome. Yeah, cool. Thanks a lot for the invitation. And I'm very honored to be here to talk about the project, our original project called Magma. The goal is pretty simple and straightforward. We really want to build the multimodal AI agent that can see, talk, and act. So, by the way, I'm from MSI Deep Learning Group, and now a principal researcher. Have been working on multimodal stuff for roughly a decade since my PhD study. So talking about multimodal AI agent, actually, this is not a very kind of well-established term. But why and what is multimodal AI agent, right? So if you look at these slides, you will see, okay, so people can do a bunch of different tasks. So people can, surf on the web and can shopping on the web and can buy a lot of stuff and play games, etc. And in the meanwhile, actually, people can do a lot of kind of domestic kind of householding tasks, right? Clean up the kitchen island and cooking, etc. And of course, you can also drive the car. So all of these tasks actually involve the perception and the language understanding and the interaction with the environment. And the multimodality here is the key to build some real-world applications to support this tedious task in the digital world and the physical world. And this is why, we really want to build a multimodal AI agent. And of course, you can see the challenge is very obvious. So we need to integrate the vision, language, and decision-making into a whole kind of single system, right? To make it be able to interact with the humans and also interact with the environment, like what we are doing daily to daily. So where we are now, so talking about multimodality, right? So it has been for a while since people talking about multimodality. I just want to briefly go through the roadmap of multimodal models since the very beginning. So 5 years ago, people talking about multimodality, it's mainly about the VL-BERT, vision language BERT, and the uniter, and etc. So all of these models actually are built on top of BERT architecture. And people usually use the image and the text as input and ask the model to predict the masked output, something like that. So this, based on this pipeline, we have seen a lot of works on top of them, and many of the work actually have been already very kind of influential. So afterwards, so we are seeing different type of work. Roughly 3 years ago, when OpenAI dropped the CLIP model, which can essentially learn from billions of image text pairs to learn a very capable vision encoder, which can be used to do zero-shot image recognition, zero-shot image text retrieval, etc. And this actually opened up a new opportunity for the multimodal community. So since then, Microsoft has a Florence and Google has a Elan, and based on all of this kind of vision foundation, people can train even more fine-grained vision foundation model or multimodal vision foundation model for different type of vision tasks like image recognition, like object detection, like image segmentation, etc. And afterwards, with emergence of the large language model, the multimodal community entered the area of large multimodal model. And some representative work like GPT-4V from OpenAI, and of course, a bunch of open source model like Lava and Mini GPT-4. And this type of work actually connect the multimodal vision foundation, like a clip vision coder with a large language model, right? And then enable very natural conversation capability for this multimodal large language model. And this type of model actually can essentially works much better to understand the human intent in whatever type of format. So this is totally different from the previous work like BERT, WhereBERT, and work clip model. And this really, inspire people to think of, so what the multimodal can do. And looking back, you will see there another kind of underlying trend behind one of these models. Start from very beginning, vision language model usually contain a very little number of parameters, less than 1 billion parameters, and trained on less than 10 million images. And afterwards, since the emergence of the clip model, so people tend to train scale up the data and train on top of up to 1 billion image text pairs. But still, the model is still very small. If you look at the clip model, actually, it's usually containing 400 megapet, right? So this is still much smaller. And the thing, people scale up not only just the data, but also a model. And you will see most of the current large multimodal model contains billions of parameters. So what is multimodal AI agent afterwards? So there is no clear definition about multimodal AI agent, but if you look at the Wikipedia and some other web page, you will see people define the AI agent that can understand the environment and also predict the actions or take actions. And more importantly, this AI agent should be driven by a goal. And likewise, so what is a multimodal AI agent? So in my opinion, the multimodal agent actually should essentially at least have two types of capability. First, the multimodal understanding, and second, the multimodal action prediction. And also, it's needed to be driven by a goal. And if we unfold this type of loop, you will see the multimodal AI agent to achieve some goal, it should observe or see the environment and take actions, and see again and take actions. And the whole process should be driven by a goal, usually conveyed through the language. That's why we're talking about the multimodal AI agent need to see, talk, and act, right? And in this talk, I will very briefly walk you through the multimodal vision foundation we have built and the multimodal large language model we have built. And in the end, mostly we will focus on multimodal agentic model, the Magma we built in the last year. So the goal is trying to build the multimodal foundation model from just a vision language understanding model to more like an agentic model. And the key ingredient is still about perception, grounding, and spatial intelligence. So at the very beginning, I want to draw your attention to this figure. I want to highlight that, the landscape of vision task is pretty complicated. So the input modality should be different format. It could be temporary or it could be static. And the modality is still not just about the vision, right? It's usually come with some other type of modality, text, audio. The task could be at different levels. It could be image level, region level, and pixel level. And the output should be both spatial and semantic. Regarding spatial, it's probably needed the model to produce the edges, boxes, and masks. Regarding the semantic, the model probably need to predict the class labels, descriptions about the visual content, right? So that being said, the whole landscape of vision task actually is pretty heterogeneous and also complicated at different granularity level. So back to 3 years ago, our team have been trying to develop a different type of multimodal vision foundation, from building better vision encoder like Unicell, Florence, region clip, and also unified encoder-decoder architecture like XDecoder, SIM, semantic SAM, grounding Dino. And right now, many of these works actually have been frequently used in the community for development, for algorithm development, or for the research community. So the reason why we want to build a multimodal vision foundation is pretty simple. So we believe that language is a common space to share the visual information. So people convey the visual knowledge through language, right? So that's why we, at the very beginning, we strongly believe, okay, we need to make the vision foundation be multimodal, not just predicting the 1,000 class levels, not just, okay, only constraint on a closed set of classes, right? And in the meanwhile, vision tasks require different type of prompt to tackle different granularity levels. As I just mentioned at the earlier slide, so vision task actually is pretty heterogeneous. We really want to have some kind of unified interface. That's why we wanted to build some unified encoder-decoder architecture. I will not delve into this definitely, but I just give you some examples. So like Project Florence, we scale up to 1 billion image text pairs and use more than 1 billion model parameters and doing the scaling up and apply to 44 different benchmarks across different vision tasks and finally achieve very good performance. And Glip, we scale up the multimodal pre-training for first grounding in the white. So people can feed an image and a textual description as input and then have very kind of fine-grained association between the regions in the image and the phrase in the sentence. And grounding dino, people can use some text prompt to ask the model to localize all of the regions in the image. And of course, we can even connect the grounding dino with SAM model to build the so-called grounding SAM to do this kind of promptable image segmentation. And with glitching for images editing, etc. And later on, we propose the same segment everything everywhere all at once. So it can even support more diverse type of prompt. So all of this works actually is trying to build a more promptable and interactable multimodal vision foundation, making this whole system to see better. And later on, we talk about multimodal large language model. So the earlier works, the multimodal vision foundations, even though they are pretty capable of recognize different type of visual content in the images, in the videos, and support different type of prompt, but it still cannot understand some complicated or sophisticated human prompt or human intention. So that's why people draw attention, pay attention to the multimodal large language model. So I still remember the figure on the left side. So the sparks of artificial general intelligence, which was written by my colleagues at MSR. So given a large language model, even without trained with any visual data, the model seems like, okay, understand the visual content in the other format. So the model can generate a code to draw a figure of unicorn. And I'm sure, okay, you guys also remember this figure on the right side. So when I first saw this image and the response from GPT-4V, actually, I was quite shocked that, okay, the model can really understand not just simply, okay, the visual content, the two cars and there are one person, there are two buildings, etc. And the model can even understand, okay, what is the humor in the images and what is the unusual part in the images, right? So this is pretty impressive when I saw this image. And back today, our colleague developed Lava, connecting the Clip model, the multimodal vision foundation with Llama, right? So to this type of open source pipeline actually can essentially mimic the behavior, the reasoning behavior, the conversation behavior of the GPT-4V back today, and it can really, okay, enable some very good capability. A typical large multimodal model or multimodal language model is look like this. So given an image, and so people usually use some multimodal vision encoder like Clip, like Florence, like Elan, this type of work to encode the image into a bunch of tokens, and then ask it and feed these visual tokens into the language model, and it also comes with some text prompt with like an answer, like a question answer format, and finally the model will produce some output. And the training procedure usually consists of two stages: first alignment and second instruction tuning or SFT. So after this type of training, actually the model can essentially build a connection between multimodal vision foundation and the language model. so that, okay, the model not only understand the visual content, but also chat about visual content and reasoning over the visual content. Back today, Microsoft also built the 5.3 vision. It was one of the first multimodal model in the 5.3 family, bring together text and images and the ability to reason over the real world images. And the design choice is also very simple. It's just simply follow the lava pipeline and adding learnable separators in between each of the row of the image. And then, okay, the model, even very small, can still achieve very good performance for multimodal conversations. And back to then, actually, when I played with the Lava, GPT-4V, and the 5.3 Vision, so I found actually one of these multimodal language model faced some issues to ground the conversation or ground, okay, the reasoning on top of the visual content in a very fine-grained manner. And on the left side, you will see, okay, so if you ask some questions, the model usually produce some incorrect answer, but also, okay, these answers are not even grounded on top of the image. And that's why actually we draw the inspiration from our earlier work, like semantic SAM, SIM, and SAM, this type of work to segment the image and add some marks on top of the visual content. And once we add some visual marks on top of the images, actually the GPT-4V can suddenly answer the questions correctly and also ground this answer on top of the visual content associated with each of the marks. So this is quite inspiring to ourselves. And we tried this type of techniques to even more type of tasks like tool use instructions, how to use this controller, and 2D game planning, and simulating the navigation. So at this point, so you will wonder, okay, why I'm talking about so many multimodal large language model. Okay, but at this slide, actually, you will see that, okay, we are seeing some connections between the multimodal visual understanding and the multimodal action taking, right? One of these tasks I'm shown here in this slide actually is trying to tell people how to do something. From the left side, okay, how to use this controller, and in the middle, okay, how to control the game agent up, down, left, right, and how to navigate in the 3D space, right, to achieve some goal. So this is quite inspiring, I would say. That's why actually starting from this point, actually people trying to extend the large multimodal model to interact with the environment from different angles. So you will see people leverage GPT-4V plus some visual promise technique, including set up mark to do the UI navigation, to do the robotics manipulation, and some other common tasks require the special intelligence. And I will give you some simple example regarding set up mark prompting for UI agent. So right, maybe 1 or 2 weeks after the release of our set up mark, an undergraduate student from MIT already built some UI agent. You will see, okay, it's pretty similar to what we are seeing right now, like the OpenAI operator and the project Maria from Google, etc. All of this work is trying to build some UI agent, right? And we've also built some smartphone GUI navigation based on similar techniques. So we ask the model to buy something for us, and then the model will click the button and pay for us. So this is really kind of mind blown back to 2023 or 2024 earlier. And in the meanwhile, actually, people further build some more kind of sophisticated web agent to traverse across different websites like Reddit, YouTube, etc. All of this type of website. And also, this type of visual prompting also enable some kind of agentic system for robotics tasks. So it can be very beneficial for robotics navigation. It can be also very beneficial for the robotics manipulation task, because this type of technique actually can enable very good grounding capability. And that's what really kind of important and indispensable for this agentic tasks or agentic systems. And again, so more and more type of works like this. So at this point, I want to highlight that, okay, we are we are right at the door of multimodal AI agent, not only in the digital world, but also in the physical world. So in the digital world side, we are seeing a huge amount of progress in the last 1 year or two. Right now, actually, we are seeing so many different type of digital AI agent to traverse for us in the website to buy something, to accomplish some task. And in the meanwhile, we are seeing a bunch of researchers work on the AI agent for physical world, mostly the vision language action model, to control the robot to finish some task like navigation task and like manipulation task, etc. And again, I want to highlight that a multimodal AI agent should be able to interact with virtual and the real world. The reason is pretty simple. Like human ourselves, actually, we can seamlessly finish the agentic task in the digital world and the physical world, and we can seamlessly do the multimodal understanding and the action taken as a single entity, right? So this is a pretty kind of good, guideline for us to build the AI system that can really have similar type of capabilities. So we ask ourselves 3 questions why we try to build the Magma. So can we build a single foundation model for both digital and physical world? And can we build an agentic foundation for multimodal understanding and action prediction? Because human as ourselves actually can do these 2 type of tasks seamlessly. And how to induce both verbal and spatial intelligence for the agent, because we observed that so to really enable to really build some intelligent multimodal AI agent, it's not only about the verbal intelligence, it's also about the spatial intelligence, because you always need to interact with the environment, and this interaction with environment actually require the model to understand the spatial layout, spatial reasoning, and spatial planning. But the problem is that, we do not have such amount of data. So how do we scale up our agentic pre-training? So that's why we proposed Magma. We want to highlight that this is one of the first work to build a multimodal AI agent as a foundation model. So we really want to make this model generic as possible as we can, so that it can be used as a foundation model and fine-tuned across different downstream tasks in the digital world, in the physical world, or even cross digital and the physical world. So as I mentioned earlier, the multimodal AI agent should be spatially grounded. So if you remember, so the earlier slides I showed set mark actually can enable the very fine-grained and grounded UI navigation, because it can essentially teach the GPT-4V, the multimodal language model, where to look and where to click. And likewise, the set mark prompting also help the robotics agent actually to look at the robot arm and to look at the target object of interest and how to move the robot arm, right? So one of these earlier works, which was built on top of set mark prompting, were related visual prompting techniques, actually inspired ourselves to think of, what is the important thing for the multimodal AI agent, so that it can essentially work well in both digital world and physical world. That's why we want to learn this type of special grounding capability through set mark for the multimodal AI agent system. And compared with the coordinate prediction, the set mark actually can significantly reduce the search space to take actions. Click a button on a screenshot actually can be solved by asking the model to select which mark to click, right? Compared with, which coordinates in the 2D grid to click. And if you look at many of the previous work, predicting coordinate actually usually have poor performance compared with the visual prompting techniques like set mark or other type of technology. And based on this intuition, actually we convert the UI navigation and the robotics manipulation task to some surrogate task set mark prompting task. So given the task like, swipe until Thursday, February 16, or given a task moving the white object above the green clothes, something like that. So the model need to predict which mark to control, which mark to manipulate. This essentially teach the model where to look at and where to control and where to take actions. And in the meanwhile, we strongly believe, okay, this agent should understand the temporal dynamics because it works interact with the environment, not only spatially, but also temporally. That's why we extend the set of mark prompting strategy to tracer mark. And we just extend the set of mark at a single slice of the temporal axis to a temporal axis, right? So based on this, we develop another surrogate task. We ask the model to if they want to, they want to accomplish some agentic task like move the orange near the orange can. This definitely is a sequential task. It's not a static one. Then in this case, the model need to produce the future trajectory of the marks that are grounded on top of the robot arm. So this will teach the model to learn a longer horizon about what action to take next. So these two techniques actually are essentially the technical part of the Magma. So it's pretty simple and straightforward. It was also very intuitive and built on top of purpose works and the inspirations from the purpose works. But the interesting point is that the UI navigation data and the robotics manipulation data actually are both pretty domain specific. If you can imagine, so these two type of data are usually very, very different and heterogeneous. So one is 2D kind of human crafted type of data, and one is a 3D type of natural environment data. And when we think of how to do the scaling up, so we've observed that human probably is a great teacher of a multimodal agent because in the YouTube or in many other kind of video data set, human motions actually are captured very well in different type of environment, like in the kitchen, like in the gym, and many or even outdoor. All of these kind of human instruction or human activity data actually are very good lessons or are very good learning sources for the multimodal agent. And if you look even closely, you will see the human motions actually are even very good for us to extract the action supervisions for the multimodal AI agent. So it covers different type of activities, covers different type of tasks, and also it captures the human motions very well. So that's why we believe, human motions captured by the videos actually are great action supervisions if processed properly. And based on this intuition, we propose some kind of trace mark generation techniques for videos, for human instruction videos, specifically in the white. So you will see given the original natural video, actually the motion is actually always entangled with camera motion. But this camera motion actually is not what we want because it does not capture essentially how the hands is moving to accomplish the task, right? That's why we propose trace mark generation algorithm to filter out the camera motion and also and always keep the motion of the end effector, like human hands, like human body, or other type of end effectors. So this is what we want. So based on this technique, actually, we can essentially extract a lot of useful informations and especially the action supervisions from a bunch of human instructional video, like Epic Kitchen, like Eagle 4D, like Cone, like How to 100 Million, etc. And in the end, we create up to 39 million pre-training data, including instructional videos, robotics manipulation, and UI navigation, multimodal understanding data. We apply set a mark and a trace mark for different data type. We set a mark enabling unified action grounding across all input. The natural image, the UI screenshot image, and the robotics manipulation and the human instructional video data. And also, trace mark is applied to the temporal data, including all of the video data and the robotics trajectory data. So based on all of this type of pre-training data creation and pre-training annotations, we in the end train a single model called Magma, which is essentially the first foundation model to support different type of multimodal agentic tasks. And the whole overall pipeline is pretty simple, nothing fancy. is just built on top the vision encoder. Here we used the CommonX XSR large. It was a multimodal vision foundation, but with a CommonX as a vision encoder architecture. And for the language model, we simply use Llama 3 8 billion. And the setup is pretty simple. We pre-train from scratch for 3 epoch on the whole entire pre-training data. And it takes the natural image, the instructional video, UI navigation data, robotics manipulation data, and mixed them together and feed them into the model. And as an output, we ask the model to decode, to generate the verbal output, which is similar to the previous multimodal language model, and the action prediction output, which could be the 2D coordinate plus some action type, or the 7DOF for the robotics manipulation. And then in the middle, this is the main part. We are invention. So we develop this kind of special annotation, theta mark and tracer mark prompting type of techniques to connect, to bridge the gap between the verbal output and the action output. And this is what we believe. And in the end, improve the performance for the Magma model to really seamlessly build the connection across different domains, across different tasks. So after this pre-training, so we evaluate our Magma model across different type of tasks in this short manner, spanning from multimodal understanding, UI action grounding and navigation, and also robotics manipulation task. So we report state-of-the-art performance across the board compared with the previous work. And our Magma model actually is the first ever model that can accomplish all of this type of task. No other works, even including GB4V or GB4O, all of this type of work actually cannot accomplish all of the tasks simultaneously in a zero-shot manner, definitely. And there's some interesting property when we train our Magma model. So the robot planning capability for tracer mark prediction shows some scaling property. On the top row, you will see with the scaling, with the increase of the data for the pre-training, you will see the model can learn better kind of robot visual planning. And the task is put the can into the jaw. And from left to right, if you look at the trajectory of the robot arm, you will see, in the end, with the full training data, the robot or the agent actually can learn, if you put the can into the jaw should not go back with the robot arm, right? And this is really, really kind of interesting to see when we first tried this example. And the model also shows very good task generalization capability. So even during the training, we do not have such kind of training data with this type of input and this type of task. For example, pick up the chip bag, put the chip bag to the Coke can, or push the chip bag to the yellow object. No such type of task at all. But the model can learn this kind of generalization ability to accomplish some kind of agentic task in the white. So this is quite encouraging to us when we first train this model and evaluate this model in this manner for robot visual planning. And again, this type of robot visual planning evaluation is really good sanity check for us to train the model. And afterwards, we fine-tune this model for different type of real-world agentic task. And on the left side, so we train a Magma model, fine-tune a Magma model on some real robot manipulation task. On the right side, we fine-tune it for some real-world UI navigation tasks, manual to verb. And afterwards, we further evaluate on the spatial understanding task and compare with different type of previous work. So as we mentioned earlier, so theta mark and trace mark in the middle can essentially improve the spatial intelligence. And as you can see here, demonstrate in the quantitative result, we evaluate on top of VSR, Blink, and spatial EVI. It shows that, this Magma indeed has stronger spatial intelligence. On the right side, we just show a single example that, Magma model actually can understand, the mass configuration compared with GP4O. Again, we apply this model and fine-tune this model on video tasks. So the video task actually essentially is require the model to understand the temporal dynamics. And the Magma model pre-training actually already learned a bunch of different temporal informations and temporal knowledge through different supervisions. And after this fine-tuning, we do not include any specific data, but we just simply follow the lava foundation, use the same amount of data for the fine-tuning and evaluate the performance for different tasks. I want to highlight the last benchmark, the MV bench. We particularly select the action prediction, action sequence, action localization, this type of action-related task. You can see here the performance is significantly better than all of the counterpart. So we want to draw the connection between this superiority for Magma model on top of an action-related subtask with the pre-training techniques we used, because we integrate the setup mark and the tracer mark, this type of pre-training to improve the action grounding and the action planning capability. And this type of capability is transferred to downstream tasks like action prediction. Even all of these tasks actually are verbal, not really action or special. And based on this model, we built some demos. The first demo we built is UI agent navigation. So we built 2 demos through the Android emulator. So you can see here, based on our Magma model fine-tuned on the AITW, the model can do some good job to accomplish the tasks on your phone. And for the robotics or real-world agentic task, so we compare Magma with OpenVLA. I want to highlight these 2 tasks actually are quite a challenge. The first task you can see here, it requires the model to precisely understand the spatial layout, because it's not like, put some object into the bowl, right? It's trying to put the object, the sausage, into very narrow space so that the task can be succeed. And on the right side, so this is an unseen task. We never trained the model to push the close from one side from the other side, but we asked the model during the inference time, during the testing time, push the close from the one side to the other side. So it can still understand what is left, what is right, and how to push the close from left to right. But the OpenVLA model actually cannot do very well. And for the video task, because we train our model across different type of video data set, the egocentric data and the set point of view data, and all of these data actually contain a lot of human instructions, supervisions, and that's why actually the model can instruct the people to do something. If you can imagine, if you are wearing some AI glass, and the model can teach you something, how to do some task. And this action is implicit, but it still can be much better compared with some previous model, which mostly learn about the verbal knowledge, right? And in the end, actually, I want to show a very interesting demo I built a while after the release of Magma. And this demo was inspired by people building, for example, some gaming environment based on GPT-4o or Gemini, this type model, but not for playing game. But here, I built some simple game and asked the model to play this game. And in these slides, you will see a task is very simple. It's just collect the green blocks, right? Control the robot to collect the green blocks. And we compiled Magma with Lava Vision and also Magma with GPT-4o Mini. You will see here, the Magma model actually can understand the spatial configuration much better than the other type of model, like Lava Vision and even GPT-4o Mini. So it can always collect more green blocks in the 2D mesh. And please note that, all of these models are never trained on top of this type of data, including Magma, including Lava Vision, and the GPT-4o Mini, I guess. So, but you can see here, some of the model actually can do very good job, like Magma, but some other model actually cannot essentially understand the special configuration or special relationship for this 2D grid or 2D maze. So in the end, to summarize, so Magma is one of the first multimodal agentic foundation model for both digital world and the physical world. And we are striving for build a single foundation model to not only do the multimodal understanding, spatially and temporally, but also the multimodal action grounding and planning. And in the end, we want to merge or fuse this type of capability to build the multimodal agentic system in both physical and the digital world. So this is an ambitious goal. I want to highlight that okay, Magma is just very initial baby step towards that goal. And I will give you some example. So Magma cannot do a lot of things. For example, Magma cannot do the reasoning capability, like what we are seeing on top of a bunch of language model and even multimodal language model. And it also cannot do planning. So because the planning is very important, but it cannot do very well. For example, if we want ask the robot to clean up this table, right? In this case, the task is not simply pick up the sausage or something like that. It's much more kind of high level and abstract. So the model need to do some planning at the first place to decompose this task into a sequence of subtasks. Unfortunately, right now, actually, this model cannot do that. And based on this, we really want to build the next version of Magma to be like this. So it's not only about multimodal understanding. It's not only about multiple atomic action prediction. In the middle, driven by a goal, the model or the system need to do the planning to decompose the high-level task, high-level goal into sub-goals, and then to execute each of the sub-goal sequentially. And for each of the sub-goal, the model probably need to even have enhanced reason capability, right? So this is what we are envisioning in the future as more kind of intelligent multimodal AI agent. And again, okay, this model is not built for the VLM. It's built for the VLA. It's need to be able to do the vision, language, and action. And in the meanwhile, we really want to have a single system that can have both multi-step planning capability and a single-step reasoning capability. At the top of this whole system, I want to highlight that. So at the very beginning, as I showed earlier, the verbal intelligence in the language model is pretty capable, and we wanted to connect this verbal intelligence with verbal intelligence. That's why we built some multimodal large language model to have a conversation to have the ability to converse with people about image, about a video. But in the next chapter, I think we are already seeing a bunch of effort to build a more kind of spatial and a temporal intelligence system. So in my opinion, I think to really build some capable multimodal AI agent, this agent should possess not only just verbal intelligence, not only just virtual intelligence to understand the visual content semantically, but also the spatial and the temporal intelligence, the ability to capture the position, location, motion of object, and interact with the 2D and 3D world along the temporal axis. So this is what we really want to build as the next chapter of the AI and the researches. So I want to conclude with these slides. So we really want to build a very kind of capable multimodal AI agent, not just AI agent. So because we really want to bring the AI brain out of the way to interact with the environment, not only the digital world, but also physical world. And in the end, just like a human, can seamlessly interact with the whole world surrounding us. So in the end, I want to highlight this work is a very great joint work by a bunch of colleagues and a bunch of external collaborators, including the former interns. And this, for Magma model, actually we already released the code and the model on Hugging Face And so yeah, so feel free to try out some demos with Magma. So thanks a lot for your attention. And yeah, I'm happy to take a few questions if you have. Yeah.
Great session. I have a question. So, on the choice of vision encoder, there are encoders these days like JAPA, which are said to be more better in terms of reasoning or planning. So, do you think that using those encoders can help in the agentic part of the multimodal agents?
Yeah, so that's a great question. So JPA, the training pipeline of the JPA actually is slightly different from, for example, the multimodal vision foundation like CLIP or even other type of models. So, so based on our earlier investigation, it turned out that okay, maybe JPA is good at, as you mentioned, okay, this kind of planning, visual planning to produce or to generate some future frames or future masked regions for the model, but it does not necessarily has very strong so-called verbal intelligence, right? So to understand or to align, to have a kind of aligned visual semantic space in the lender representations. So this part actually is also very essential to build a multimodal AI agent because it requires to understand, okay, the task and okay, translate this task into some kind of more fine-grained language representations, and then okay, produce the output accordingly. So I think right now there's still some gap in between. So both type of vision encoder, the clip or the JPA or video JPA, as you mentioned, actually they have the pros and cons. So in the end, as I highlighted in these slides, so I think we really want to have some single vision encoder which can process not only just verbal intelligence, not only about okay the spatial temporal intelligence or visual intelligence. So we really want to build a very strong kind of vision encoder or vision tokenizer come with verbal, visual, and spatial and temporal intelligence. But right now, unfortunately, we do not see a single vision encoder that can process all of this type of capability for supporting the multimodal AI agent system. But right now, the reason why we want to choose the clip or clip-like, the convex XL large is also kind of in a clip objective. The reason is pretty simple. So it already have a strong verbal intelligence. It has a line of visual semantic space. And I believe, okay, in the near future, people will think of, okay, how to combine the VJPA or JPA type of pre-training with this clip type of pre-training to build more kind of connection across different intelligence aspect. Yeah.
Great. And one more question. Do you think that unified pre-training is better, like a combined vision and combined language encoder, as compared to separate encoders for both, like something that can combine both?
Yeah, that's a very good question. I think that's a really good question. So honestly, I do not have an answer yet because we had a lot of discussion in our team as well. So they both have pros and cons. So if we have separate one, so then okay, it does not require end-to-end, right? Training the whole system. And usually okay, it requires less compute resources, and you can first get a very kind of capable vision encoder, and then connect this vision encoder with language model, and then SFT, and even right now actually maybe RL training on top of it. So this will give you some good performance, right? So and but in the meanwhile, if we think of for example human, right? So usually okay, we link the whole system, our brain, our cognition system actually end to end. It's not like okay, we first separately learn some visual intelligence or something like that. We usually learn the cognition ability end to end. And but the problem is that okay, so in practice, it's very hard because, okay, you need to build a very kind of huge or big giant system. It contains a lot of parameters, and also the training data actually is usually imbalanced. So for example, image dispatch, we can get a huge amount of image dispatch for clip pre-training, but we probably cannot get the similar amount of data for robotics tasks. So this will give us some kind of challenges, some kind of very kind of inherent challenges that, okay, if we train the whole system end to end from scratch, so we will always face some issue about, okay, the training instability or training data imbalance problem. And also it requires much larger amount of compute because we always need to tune the parameters and the parameters in the whole system end to end. So there is no clear answer. Even though, okay, there's some AI tries, right, from the ADX AI. So they simply, okay, feed the pixel as input and try the best, okay, to reduce the size of the vision encoder to just a patch embedding. But in the end, actually, they seems like give up because it's really type of compute consuming, and it's not that easy in general. But I believe end-to-end is very important, but I also do not have a very strong bias that, okay, we need to only use one transformer decoder to ingest all of the modality input, the visual data, the pixel data, the audio data, the 3D information, the point cloud, etc. There's still some kind of sweet spot in the middle, I believe, but I do not have a clear answer, honestly. So it's really require a lot of empirical study and the set comparison. But the data is very important, and especially after we build a Magma, I think so. How to create data, how to create clean data and train the model with the correct objectives is really important to to squeeze out the intelligence for the model. So yeah.
Thanks. There are questions in chat as well, and a hand raised, so you can unmute and ask the question.
Yeah, thanks for the great talk. So my question is like, having gone through the Florence two paper and having gone through your talk now, is it safe to say coming up with uh, synthetic pipelines to generate data is the unlock that we are seeing for new age multi model models, and if that is true, then what do you feel the greater unlock would be for reasoning and planning in a similar sense?
Yeah, I think that's a very good question. So yeah, I like you said, Florence too. Yeah, so my colleagues did that. So I think right now actually more and more people recognize that, okay, so the data is really important. So and if you have very high quality data which align with your tasks of interest, actually you usually give the best performance compared with the model tweaking, etc. Of course, modeling design is also very important, right? But to get back to your question, I really believe, okay, so given the existing data set or some initial annotations, how to grow this initial data set and the annotations to more fine-grained, more sophisticated annotations, and okay, more aligned annotations with your tasks of interest. This is really kind of personally, I think this is really important. Like you can see from Florence too, right? So they built a huge amount of data set which contain the fine-grained annotations, box, a mask, etc. And like you are seeing here for Magma, actually we build some synthetic annotation, not necessarily the synthetic data, but more like a synthetic annotations, like setter mark and tracer mark. And we found this set mark and trace mark. Actually, we did not show here according to the ablation. This set mark and trace mark in between of their verbal output, verbal supervision, verbal annotation, and the action supervision actually can essentially help us to build a single model and improve the performance across the board. So I in my opinion, I think to build the multimodal, intelligent multimodal models. So how to start from the initial supervision, initial annotation, like very kind of short caption of the image to enrich the one, and how to start from the enriched one to more kind of comprehensive one, covering not only just verbal part, but also spatial part, etc. This is really kind of important. And talking about the reasoning and the planning, so for reasoning, I think one of you guys also saw a lot of works doing multimodal reasoning, and starting from Queen VR2 or 2.5, and then use GRPO type of thing, and train some kind of model to do mass reasoning, right? For or even kind of fine-grained visual ground reasoning, etc. So I personally I believe we also can come up with some method to build some good and high quality and factual or authentic kind of reasoning data on top of the existing annotations based on existing models, if processed properly, as I mentioned. So only if we process the data properly, then we can probably squeeze the information from the synthetic data and make the model work for our tasks. So I saw a bunch of work, even some of the work actually starting from the DeepSeek, the language model, reasoning language model, and come up with some methodology to synthesize some multimodal reasoning data and continuously tune this LLM reasoner to do multimodal reasoner. So even like Lava, right? So the synthetic data is also very important. Connecting the vision coder with the language model by come up with some data synthetic pipeline. So this gives us some hint, like we already have a lot of building blocks, very capable language model, very capable multimodal language model, very capable vision foundation model, like Grounding Dino, like Florence V2, many of them, right? Like SAM, etc. I believe, we have given all of this type of toolkit. I believe it's much easier for us to come up with some pipeline to build synthetic data to really, achieve even the next level of the intelligence on top of this existing very capable model already. So the reasoning and the planning, actually, we are also considering thinking very heavily about the planning. So how to do the planning, right? So how to collect the data for the planning. So this is also what we are think of. And one of the data sources is the video data. So how we convert this video data into the multi-step planning data to tell the model, given the current observation, current context, and given the goal, high-level goal, and what's the most likely next step actually do to finish this task as soon as possible and as successful as possible. So to conclude, I believe, so we can leverage the existing toolkit, different type of models, different type of tools to really build some very good high quality synthetic data, even probably better than human annotators. So this is what I believe. Yeah.
I have one more question. So when you are annotating the motion data sets and you are like marking the positions from where it started and what is the end, do you think that these models should be able to like learn these steps like implicitly instead of being manually labeling them, like providing the manual annotations on how the steps are working, and like the representations are automatically learning just by seeing the video that what action is being performed in this video?
Yeah, that's a very good question. So by seeing the video and for example, implicitly learn how to take action. Actually, this has been already studied in a bunch of literatures, and even one of our earlier work like LAPA. So ask the model to predict the future latent action token or something like that. So this was another kind of strategy or pipeline people are studying. In general, I think I took some inspiration from the next token prediction language model, honestly. So this kind of future trajectory planning or future trajectory prediction actually forced the model to understand better their past, understand better the goal, understand better about the spatial configuration in the current observation. So this is what I learned and took inspiration from the language model in general. As Ilya mentioned, okay, so next token prediction actually probably is very simple and primitive, but this type of next token prediction actually can force the model to understand past. And likewise here, so predicting the future trajectory, not only make the model to be able to learn or capture the past motions, right? But also, okay, make it possible for the model to predict the futures. So this is what I believe. And there are different ways to learn from a video. And like the video JPA we just discussed, right? So this is another way to predict the future, the masked regions prediction or something like that. And the future prediction is not only just for the trajectory. It probably can be applied for the latent prediction, latent feature prediction, or masked region prediction, etc. And essentially, I believe it shares the same kind of significance to the next token prediction in language model pre-training. So the video data itself is spatial and temporal, and the spatial part actually we already learned a bunch of object detection and visual grounding model. But how to learn this type of temporal intelligence? I believe, okay, this next something prediction is very, very kind of essential to learn this type of temporal intelligence, no matter implicit way or explicit way. Yeah, this is what I believe. Yeah.
There's one question in chat as well of the meeting.
Oh, I am not sure.
I can read it.
Oh, yeah,
So,
thank you. Yeah, thank you.
the question is, do you propose to look into emotional intelligence capabilities for interhuman or HCI interactions as well? If you would, how would you attempt to imbue and evaluate such capabilities?
Yeah, that's a very good question. Emotional part, right? So I chatted with some robotics guy, and before that, actually, I didn't notice much about the emotion type of intelligence. But after that, actually, I thought, okay, so if you really want to build some intelligent AI agent that can interact with human, that need to interact with human, actually, this kind of emotion awareness actually is very important in my opinion, because it's really want to bring, okay, some intimate type of interaction with human, right? So I honestly, my background is not for this part, but I believe, okay, once at one point, okay, if we already achieve very good capability for this multimodal AI agent to interact with human, interact with environment, or interact with both human and environment, and the next very important step to make the agent at the next level is about the emotional intelligence. So how to make sure, okay, when this robot, especially the humanoid robot, the domestic humanoid robot, right? When you put it in your home, then how to make sure, okay, you feel comfortable to interact with them. You feel comfortable that, okay, this agent or this robot actually residing in your house, in your home. How to how to make sure, okay, you feel still safe. I think all of this require the agent to build some trust, mutual trust with human, not only through the capability, not only driven by capability, right? Help you clean up the table or something like that, but also through the communication, the verbal communication, but also some kind of other gesture or other kind of expression, face expression way or something like that. So this is what I believe will be very important after we achieve the necessary capability for the multimodal AI agent to interact with the human and the environment. I talking about the benchmark, I do not have idea, honestly. So I think indeed, I believe, okay, this will be very important building block for the next generation of the AI agent in our daily life. Yeah. Cool.
Great. If you don't have any other question, we can conclude the session. Thank you so much, Dr. Yang, for your time.
Yeah, thank you very much for the great questions. Yeah, and yeah, I'm quite honored to be here to share our work. Yeah, thank you very much for your invitation and for your host, Ahmed. Yeah,
Thank you. Take care.
Yeah, thank you. Take care. Yeah, thank you. Bye.